So, chapter 10, ladies and gentlemen, has the title Liquids and Solids. What's missing in the title?
Gases.
Gases. Okay? Gases are in their own separate chapter, which we have already covered. Gases were back in chapter 5. Okay? Why do they get their own separate chapter? Because they behave so differently from liquids and solids that they get their own chapter. Liquids and solids behave in a very relatively similar way, so we put those two together. Okay? And some of what we're going to do today is going to be review, and we're going to tie some of these concepts into some real life application today. Okay? Makes it a little more interesting. So, when I say liquids and solids have things in common, what am I talking about? Well, first of all, they are very incompressible, whereas gases are very compressible. Liquids and solids, not much, if at all. Okay? Their densities remain relatively constant, unlike gases, where if you change the temperature, you can change the density. Okay? And any similarity that exists between liquids and solids is a factor of how they are held together. Okay, the forces that hold the particles together, and that's what we're going to start off talking about today. Intermolecular forces. This is a topic you should have covered, although it may have been brief in your Chem 1 class. Okay? And before we talk about the types of forces, let's talk a little vocabulary here. This is good SAT vocabulary prep. What does the prefix inter mean? James, do you know? Nope. Between two different things. The one you're thinking about is the other one we're going to talk about today, which is intra. Intra, with an A, means within one thing. Inter means between two things. Intra means within one. Now, think about it, okay? What holds any compound together, okay? And I'm talking intra first. Any compound, there's only two types of forces that hold a compound together. What are they? Ionic and covalent. Ionic and covalent bonds are intra, okay? Meaning they hold one compound together. Inter, there are three types, okay? And let's talk about each one individually, okay? Here's your first one. Dipole-dipole attraction. Let's review a little bit. What does the word dipole mean to you? Okay, something that is polar. All right, well, tell me this. If I say that a molecule is polar, I mean, what does that actually mean? Yeah, there's an imbalance of electrons in the molecule. The electrons are sort of grouped on one side of the molecule. Okay? That's what it means to be polar. Now, make sure, just because we're in a new chapter does not mean that you can forget all of the shapes and stuff like that we just finished up, because you will be expected to figure out whether something is polar or not. And you can't figure that out unless you know how to draw it and determine its shape. Okay? But I'm going to draw a very fancy drawing of a molecule. Are you ready to see my artistic skill here? Wow. That's a molecule right there. It does look like a potato. If I tell you that this is a polar molecule, that means one side is a little bit negative and the other side would be a little bit positive. Okay, meaning the electrons are sort of glommed on to this side. Okay, now it's a potato magnet, yes. Dipole-dipole attraction is a type of intermolecular, okay, meaning between two molecules. What would be existing between within this one? We would call that a what kind of force? Intra, okay? Dipole-dipole attraction means, I'm representing it with this sort of dashed line here. The positive end of one molecule is going to be attracted to the negative end of another one. That's dipole-dipole attraction. One specific type of dipole-dipole attraction is called hydrogen bonding. Okay? So let me just make sure this is clear. If I give you a molecule and it's polar, it will have dipole-dipole attraction. It might also have hydrogen bonding. It might not, but it could. Right? It's a specific type of dipole-dipole attraction which, as you can tell by the name, involves hydrogen, but it's not just hydrogen in anything. The molecule has to have hydrogen and one of these three elements: nitrogen, oxygen, fluorine. What do you think is so special about those three? They're very electronegative. What does it mean to be very electronegative? Attracts electrons strongly. Okay? So, here's the thing, and this is a tough concept for some people. Guys, you are going to have questions on multiple choice, free response, all over the place where you're given a compound and asked to identify what kind of forces are holding it together. Well, first thing I would do, if it's covalent, figure out, is it polar, first of all. If the answer is yes, it's polar, what does that mean to you from the previous slide? It has what kind of attraction? It has dipole-dipole. If it's polar, it's got dipole-dipole, the next thing you want to figure out is, does it also have hydrogen bonding? It might not. Right? So tell me this first. I want you to look at these two Lewis structures. Does this one on the left have polarity? Is it a polar molecule, yes or no? Yes. Okay. What's the shape on this one? Trigonal planar, but not all terminal atoms are the same element. So this is polar. And if it's polar, what does that mean? It has dipole-dipole. I'm going to abbreviate it as dip-dip. Okay? Is this one polar or non-polar, the one on the right? It's also polar. Okay? So it also has dipole-dipole. Now, do you all agree that both of these compounds have hydrogen? Okay? They also both have oxygen. Wasn't that one of the three elements needed for hydrogen bonding? Okay? But I am telling you that one of these has hydrogen bonding and the other one does not. Let's read the statement here. It says hydrogen bonding only, in bold, occurs if hydrogen is chemically bonded in an intramolecular way to one of those three elements. Which one of these does not have hydrogen bonding? The one on the left. Why? Because the hydrogen is not actually bonded to oxygen. So this molecule has dipole-dipole only. What about this one? Yes. So this has dipole-dipole and hydrogen bonding as well. Okay. Guys, that's a really tough concept for some people. A lot of people will see hydrogen and just immediately assume hydrogen bonding. That is not always the case. Okay. These are just some pictures of what intermolecular forces can look like. This is water, and I actually have a physical model of this as well. All right, this may be hard to see from where you're sitting, but the red pieces here, and I'll walk around with this or I'll pass it around. The red pieces represent oxygen atoms. The white pieces are hydrogen atoms. What do you think these green pieces represent? What kind of bonds? Okay. Here's water. The green piece is going between one water molecule and another water molecule. So what is the green representing? An intermolecular force. And tell me, what kind of forces does water have? Dipole-dipole, does it have hydrogen bonding? Yes, it does. Okay? If you were to look at ice under a microscope, okay, or liquid water, this is essentially what it would look like. Okay? Pass it around. Now, there is a third type of force. Why did I put this one last? Because it is the weakest of the three. Okay, now I want to be absolutely crystal clear about something here. All covalent compounds. All covalent compounds have London dispersion forces. Let me say that again. All covalent compounds have London dispersion forces, including the ones that we just looked at. However, if something is nonpolar, that's all it has. If something is nonpolar, it's not going to have dipole-dipole. It's not going to have hydrogen bonding. Okay? Let me make sure that's clear. All covalent compounds have London dispersion. If it's nonpolar, however, that is the only force that it has. Now, here's the thing, okay? You probably learned about London dispersion forces in Chem 1, but you may not have actually learned what it physically is. Okay? And I'm going to give you just a very simple example, okay? Let's use this molecule. I use this one a lot as an example. What's the name of it? Methane. Okay? What's the shape? Tetrahedral? Polar or nonpolar? Nonpolar. Can you please tell me what does it mean for a molecule to be nonpolar? Equal distribution of what? Electrons. There is no imbalance. They're equally distributed. Well, tell me this, guys. In a molecule where there's electrons all over the place, do electrons sit still? Can they move? Yes. Okay? Now think about it. Okay? If electrons are constantly in motion, isn't it just possible that maybe just for a split second, all the electrons are not perfectly evenly distributed? Isn't that possible that even just for a nanosecond, they're not perfect? That's possible. In fact, that's what happens. Okay? Yes, this is nonpolar. Yes, that means even distribution. But for an instant, a nanosecond, maybe not even that long, the electrons could be imbalanced. It's called an instantaneous dipole, okay? Meaning it's polar, but only for a split second. So let's imagine that just for a split second, this molecule is a little bit more negative on the right and a little bit positive on the left. Well, let's say there's another methane molecule next to it. if these guys are close to each other and the right-hand side becomes, even just for a second, a little bit negative, what do you think that's going to do to this one? Okay, well, if this is usually nonpolar, for a split second, this one might become what kind of charge on the left-hand side? Positive. And a little bit negative on the other side. Okay? It's not for longer than an instant. And guys, because it is so short-lived, that's why it's a very weak force. Because it doesn't last very long. Okay? It induces a dipole in the atom next to it. Sometimes London dispersion forces are called this very, very wordy name. Induced dipole interaction. Takes forever to say. Just call them London dispersion forces. Okay? But that's what a London dispersion force is. It's a momentary dipole. Why are they so weak? Because they don't last very long. That's why. Okay? Now, this is a super duper important vocabulary word. Write it down. Have the slides, circle it, draw exclamation points around it, stars, flashing lights. Okay? I don't know how you draw flashing lights, but you know what? Figure it out. Okay? Just try. Here's the deal. Okay? I just showed you an example of where one methane molecule was inducing a momentary dipole in the molecule next to it. Well, ladies and gentlemen, certain molecules are more polarizable, more easily pulled into that dipole than others. Okay? Think of it like peer pressure. Some people are more susceptible to peer pressure than others. Okay? Polarizability means how likely is a molecule going to be pulled into a instantaneous dipole, and you'll be asked to predict which molecules are more polarizable than another. Okay? And guys, honestly, it comes down to the number of electrons. Let's say you have a question like this. Okay? Free response situation that you will see questions very similar to this. Okay? CH4 versus CBr4. Both tetrahedral. Both nonpolar. But I'm telling you that they're not quite the same. Okay? Would you agree that they both have London dispersion forces? Does either one of them have like dipole-dipole or hydrogen bonding? Nope. So they both have London dispersion forces only. Okay? Well, let's say that this free response question says this, or asks this. Which one of these molecules has the higher boiling point? Okay, well, before we even start to answer that question, what does it mean to boil something? Okay, what kind of bonds? Inter. When you boil a pot of water, okay, and vapor starts coming out of the pot, what's in that vapor? H2O. Not hydrogen gas and oxygen gas. When you boil something, you're not breaking intra, you're breaking inter. Okay, now think about it. Use common sense. If two things are very tightly held together, okay, is it going to take a higher temperature or a lower temperature to finally break it? Higher. More heat will be required. So essentially, when I say which one has the higher boiling point, I'm asking you which one has the stronger intermolecular forces. Well, you guys said they both have LDFs. London dispersion forces. But which one of these has more total electrons in the molecule? Okay, if it's got more electrons, it's more polarizable, it's more easily induced into that instantaneous dipole. Here's what you would say. Okay. First of all, you draw their Lewis structures. You cannot forget how to do that. You would say, because both of them are nonpolar, they have London dispersion forces only, but use this $1,000 vocabulary word. CBr4 contains more electrons, thus it is more polarizable, which means its London dispersion forces are a little bit stronger. Not a lot, but a little bit. Enough to make it have a different boiling point. Okay. So let me summarize that again. You draw them both out. Because they are both nonpolar, they both have London dispersion forces only. But because this is simply a larger molecule, it is more polarizable. And thus its London dispersion forces are a little bit stronger. Okay? So, the bigger the molecule, the higher the melting or boiling. Doesn't matter. It doesn't matter if I ask you boiling or melting. I'm always still asking you the same question. Which one has the higher, the stronger intermolecular forces? Your textbook may use this term. You may see this term sometimes. London dispersion forces are sometimes called van der Waals forces. You're welcome to use this term. I'm going to use this one though. Your choice. They mean the same thing. All right, let's get into some real life application here. Now that we've got the basics of intermolecular forces down. Ladies and gentlemen, intermolecular forces are responsible for a lot of behaviors that you see out in nature, okay? With elements, compounds, okay? There is a creek near my house, and in the summertime, there are always hundreds of these water bugs on the surface of the water. They're not floating. They're actually literally sitting on the surface of the water. I'm sure you all have done this demo before. You can actually get a paper clip to, it's not floating, because floating involves actually being in the water. It is literally sitting on top of it. Both of these behaviors are a factor of a result of what's called surface tension. Okay? The resistance to breaking that plane. And ladies and gentlemen, surface tension is a result of intermolecular forces. And use your common sense. If something is very tightly held together, do you think it will have a high surface tension or a low surface tension? High. Things that are loosely held together, a water bug could not sit on it. Okay? And think about what's holding a water molecule. If this is, just pure water, what's holding water together? Do we have dipole-dipole? Yep. Do we have hydrogen bonding? We also have London dispersion. We have all three. Remember I said all covalent compounds have London dispersion. Okay? There's another one, which I'm going to jump right to the picture of this, and then I'll come back. Okay? Some of you may have seen this in doctor's offices. Some of you may not have seen this. Okay? Let's say you go in for a checkup, and your doctor needs to test your blood for something, but he or she does not need to, take it from your arm. They don't need a whole vial of blood. They just give you one of those little finger pricks. And you get just this teeny tiny little bead of blood on the tip of your finger. Sometimes to collect that blood, that small amount, they will use what's called a capillary tube. Okay, and that's what's being represented here. This is a very blown up picture. of a capillary tube. It's essentially exactly like a drinking straw, except it's made of glass, and it's really small, okay? Like, you know those stirrers that they use for coffee? It's even small. It has a smaller diameter even than that, and it's made of glass. And they take these teeny tiny little capillary tubes, and they just stick it right into this little bead of blood on your finger, and the blood spontaneously just goes up the tube. And they hold the tube, the blood does not flow out either end, it stays in the tube, and then they've got this nice convenient little way to carry your blood around. Okay? Now, capillary action is describing the blood spontaneously going up the tube. Well, let me tell you this, or you tell me actually. Blood is 85% what? Water. Is water polar or non-polar? Polar. Okay. Well, the glass that they would use with a capillary tube is also polar. And I know we haven't talked about this much, but polar and polar, the two things that are polar like to be near each other. Yes, because they would have dipole-dipole interaction. Okay. Well, you may or may not have learned about this in biology, I don't know. There are such things called cohesive forces and adhesive forces. Okay? If these little white dots represent the water molecules in your blood, and they're polar, and this is the glass that's also polar, okay? Adhesive forces mean something sticking to something else. Water sticks to glass very well because they're both polar. Does water stick to itself? Yes. What's holding it together? No. What kind of forces are holding these water particles together? Intermolecular forces. Those are called cohesive. Something sticking to itself. Okay? And ladies and gentlemen, if you could watch in like super duper slow-mo the blood rising up this tube, what you would literally see is a water molecule sticking to the side of the glass, adhesive, and then because the water is also stuck to some of its buddies, cohesively it brings its buddies along with it. And then this next one sticks to the glass, and he brings some of his buddies along with him. And so on. Adhesive, cohesive, adhesive, cohesive, and slowly it crawls its way up the tube. Okay? The point is, the stronger the intermolecular forces, the better this will happen. What if this tube wasn't made of glass? What if it was made of plastic? Do you think it would work? Why? Because most plastics are non-polar. Polar and non-polar do not like to be near each other, so that would not work. All right, here's another one. For any of you that are car enthusiasts, or I should say any of you that have a car nice enough that you actually care what it looks like on the outside. I don't have that problem because my car's a piece of crap. Okay? But in the summertime, people that have really nice cars, they'll get the car washed professionally and they'll have it waxed and it makes the paint job look really, really nice. Okay? If any of you have ever seen a freshly waxed car, Aditya, hush please. If any of you have ever seen a freshly waxed car and then it rains, have you ever seen what happens? Yeah, the water, they form little beads and then they just run right off. Okay? Alright? I want you to imagine that this red layer here is a layer of wax. Okay? And this is water right here. Okay? This is a water. This is a bead of water. Water's polar, right? Okay? Waxes, oils, Fats fall in this category too. All of these kinds of molecules, ladies and gentlemen, are non-polar. Polar and non-polar, do you think they like to be near each other? No, sir, they do not. So we have cohesive forces at work, because water likes to stick to itself, but it doesn't stick to the other thing. There's no adhesive forces at play here. So what you get is these beads. This water is trying to minimize its contact with this surface, and so it forms these little beads. Okay. There's a product out there that's really, really neat called Rain-X. I don't know if any of you have ever used it. It's essentially a wax or an oil, and you put it on your windshield. And the beauty of it is it's a non-polar substance, and so when it rains, it's so effective, you don't even have to use your windshield wipers. You don't have to use them at all. I mean, in a strong rainstorm, you can, if you have Rain-X on your window, the water just flies off. It's really cool. Okay? Try it. It's neat. Okay? Now, in a ridiculous scenario, we're going to reverse this. I want you to imagine that we have not a non-polar surface, but a polar surface, like let's say just pure glass that's polar, and let's say it's raining canola oil. Okay, I don't know why that would be happening, but yeah, I know. Check your weather, people. Make sure there's no canola storms coming our way. You'd see the exact same thing. Non-polar oil on a glass surface. It would bead up just like that.
Even though it's not cohesive?
It is cohesive. Things that are non-polar are held together how? With what? With London dispersion forces. They're very weak, but they are there. So even if it was raining oil, there are cohesive forces. They're weak, but they're there. Okay? Now, somebody asked the question last class, I thought this was very clever. If glass is polar, how do you get something like that Rain-X product, which is non-polar, how do you get it to stick to the glass? It's my understanding, first of all, not all glass is polar. For lack of a better term, I believe that any glass that is put in the windows or windshields of a car are depolarized. I'm making that word up, okay? But I am pretty sure that the glass that is put in cars is not polar, non-polar, okay? Here's another one. Do you know this word? Viscous. If I say a liquid is very viscous, can you give me an example? Someone just said it.
Syrup.
Honey, syrup, molasses. Okay? Things that flow very slowly. Okay? Again, all a factor of the strength of intermolecular forces. The stronger the force, the more viscous it will be. Okay? What about oil? Would you say oil is viscous? Really?
Yes.
Compared to water? Okay, compared to water, I would say oil is viscous. But, and this is a question that's been on the AP exam multiple years, oils, fats, waxes, these are all what kind of substances? Non-polar. Non-polar. Non-polar things are held together with what? London dispersion. I thought London dispersion forces were really weak. Aren't they? So why would oil be more viscous with its weak London dispersion, more viscous than water, which has London dispersion, dipole-dipole, and hydrogen bonding? That seems backwards, doesn't it? Things that have strong forces are very viscous. Ladies and gentlemen, what does the word polarizability mean? Its ability to be pulled into polarity. Ladies and gentlemen, oil molecules and fats and waxes are huge molecules. Gigantic. If a molecule is really, really big, does that make it really polarizable or not so much? Really polarizable. Okay? Ladies and gentlemen, the gist is oils, the molecules are so large that their London dispersion forces, as weak as they are actually stronger than all three of the forces put together in water. Okay? That's strange, I know. I know. But the gist is, the stronger the force, the more these things all tend to occur. Okay? Now, I'm just going to ask you one last little sort of review question, and then we're just going to take a little break. I'm going to draw some things for you.
I wish we'd have a draft.
Okay. This is sort of to wrap up what we've been talking about, and then we'll take a little break. Okay? I've drawn 3 structures for you. The question is, which one has the highest melting point? Before you can even think about giving me a final answer, what do you need to determine about each one? Bonds. What do you mean bonds? Intermolecular forces. Okay? Alright, well, the way to start that is by determining, are they polar or not? Non-polar. So this one is going to have what? London dispersion only. Okay? So LVF only. Okay? What about this guy? Dipole-dipole and what else? London dispersion. Okay? Why doesn't it have hydrogen bonding?
Because the A's are bonded to the F.
Okay? So London dispersion, dipole-dipole. What about this guy? All 3. So what's the answer? The last one. This is going to have the highest melting point. Why? Because it has the greatest intermolecular forces. Okay? Okay. So the first section that we just did was essentially about liquids. The next section is essentially about solids. And the last part of this chapter, which we're not going to get to today, is about the interaction between them. Okay? So, ladies and gentlemen, there are essentially 2 types of solids in this world. Amorphous and crystalline. If you have the prefix or the letter A in the front of any word, what does that mean? Not, or lacking. Okay? What does this word form mean? Not the definition of the word to morph, but what does this, like, sort of Latin prefix or shape? Without shape. Okay? Amorphous solids, and glass is an example, are structures, are solids that if you looked at them under a microscope, you wouldn't see any pattern to how they're assembled. It's just a mishmash of atoms and molecules all mushed together. A crystalline solid means it has some kind of pattern to its structure. Okay? For example, okay, that would be an example of something that has a pattern to its structure. We call it a lattice. We've seen that word before. Okay? Now I want to make sure you understand, just because I say that a solid has some kind of a pattern, a crystalline solid, it doesn't have to be cubes. For example, would you say that this has a pattern to it? Yeah, it does. It's not, they're not cubes, but it is a pattern. Okay? How about this one? Would you say that has a pattern to it? Yeah. Again, it's not cubes, but it is a pattern. These are crystalline solids. Okay? Now, if the compound is ionic, and how would you know that, by the way? Metal and non-metal, okay? Forgive my lack of artistic ability here. But let's say that the pattern is a cube stacked onto another cube, etc., etc. My best attempt at drawing a three-dimensional box. Okay? If it was an ionic solid, like NaCl, for example, you need to know what are at the corners, okay, or junctions. These are called lattice points. And if it's an ionic solid, what's at the lattice points are the actual ions. Like if it's NaCl, this corner is going to have an Na+. What would this corner have? Okay, why wouldn't another Na+ be right here? Yeah, like charges repel. Na+ at this corner, Cl- at this corner, Na+ at this corner, so on and so on. Okay? So in an ionic solid, ions are at the lattice points. Whereas the word molecular, ladies and gentlemen, I want you in your mind to tie these two words together. The word molecule or molecular means covalent. Do you have ions in a covalent compound? No. But something like ice, which is water, you know, that's covalent. It has a structure to it. It wouldn't have ions at the corners. Any ideas what would be at the corners? Since there's no ions, what would be there? Yeah. Good reading. Discrete and covalent bonded molecules. It means, let's say we're talking about ice. It means entire H2O molecules are at each corner. H2O, H2O. Okay? Now just to be clear, what's holding this lattice point together to this lattice point? Am I within a molecule or between molecules? Intermolecular forces. Okay? What about when I had the ions? I had Na+ here and Cl- here. That's intra. That's an ionic bond. Yes. If you want to be really fancy, we would call this an electrostatic attraction. Okay? But it is an ionic bond. Okay? On metals, let's say I had a bar of gold. Ah, if only. Okay? Just a straight bar of gold. Gold is a solid, right? Okay? It's not a compound. It's just a pure element. Okay? What holds metals together? They just call it metallic bonding. I will tell you guys that your textbook goes into a lot more detail on this than you need to know. What you need to know about metals when they're in solid form is that they have what's called an electron, a sea of electrons, meaning electrons can flow very easily. Does that sound like something that can conduct good electricity or poor electricity? Very good. Metals are very good at conducting electricity because, and heat, because they have electrons that can freely flow around, which is why we do not put a paperclip in an electrical socket if we know what's good for us. Okay, now, there is a special little section in this chapter that is just about the element carbon, because carbon is a very bizarre element. Ladies and gentlemen, carbon exists in 3 very, very different forms. If you were to dig carbon up out of the ground, most likely it's going to be in the form of coal, like charcoal. Okay? It's amorphous. It has no structure to it. Hence, there's not a lot to talk about. It's boring. We're moving on. Okay, the 2 more interesting forms are diamond and graphite. Okay? Do diamond and graphite look alike? No. Do you think they feel alike? No. They are different in almost every way except for the fact that they are made of the same element. Okay? This model that I held up earlier, this is diamond. Okay, this is a model of what diamond looks like. And each one of these little black pieces is a carbon atom, and the green pieces are the bonds between the carbon atoms. And I want you, and I'm sorry for those of you that are in the back and may not be able to see this, for those of you that are close enough, I want you to focus in on one of the black pieces. Focus in on it. And look at the green parts attached to it. What shape is that? There's 4 things coming off of it. Tetrahedral. Each one of these carbons in diamond is tetrahedrally bonded to other carbons. Okay? Now, it says on here, you probably already know this, diamond is the hardest natural substance on Earth. It's also an excellent insulator. What does the word insulator mean? Okay, a poor conductor of electricity and heat, which means if we had unlimited resources and lots of billions and billions of dollars, I should make my travel mug for my coffee out of diamond, because that would keep my coffee nice and warm for a very long time. Okay? I should do that, you know, with all the billions that I have stashed away. All right? We should all build our homes out of diamond. Okay? Warm in the winter, cool in the summer. Okay, forget about the fact that you're living in a see-through house, but whatever. Why is diamond such a hard substance? Because it is held so tightly together. And look at this. Just look at it. Okay? Compared to, listen, compared to, say, this model. If this one has lots of room for electrons to flow around in, does it look like there's much room for electrons to move around? If electrons can't move around, it's not going to conduct heat or electricity, and that's why, because it's so tightly bonded together. All right? So I'll pass this one around. This is what diamond looks like. This is graphite. Where do you find graphite?
Pencil.
In your pencil, okay? But this is what graphite looks like. Very different from our diamond, okay? Now look at it from 2 ways. Do you see these little hexagons? Okay? Hexagons join to other hexagons, and then turn it this way, and you've got these layers of hexagons. And guys, if you ever get a chance, if you ever have an interaction with a locksmith, hopefully you won't, because you only use those when you get locked out of your house or your car or something, or you break a key off in the lock, but whatever. If you ever come across a locksmith in your life, ask the locksmith if you can have a little small sample of his graphite. Okay? It's going to be a really weird question, I know. Okay? But years ago, the seniors, this was like 5 or 6 years ago, seniors thought it would be just a hilarious senior prank to put hot glue in all of the locks of just the math classrooms. Okay? I think that's a pretty jerk thing to do, but that's just me. Okay, so they had to call the locksmiths. And of course, I'm the only one that's like, yes, a locksmith is coming here. I can have access to graphite. Okay? So the locksmiths come in there, they put some kind of something in the locks that dissolves the glue, I don't know what. But then, graphite is a really bizarre substance when it's in a powdered form. So in your pencil, it's, in little sticks. But if you were to grind it up in a powder, it is the weirdest substance. If you put it on your hands, it feels almost like your hands are wet. Like you can rub them together and it feels almost like you have oil on your hands, but you don't, and it's dry, but it's slippery. It's weird to describe a solid as slippery, but it is. And locksmiths use it when they, like someone's having trouble getting a key gets jammed or something. It's almost like putting oil. It like helps make it slick. Okay? So I trot down to the math wing and I, encounter the locksmith and I'm like, oh, hello. Can I please have some of your graphite? And the guy thinks I'm so weird. But he let me have a little of it and I'm there playing with it. Anyway, I made a big mess. Whatever. I thought it was fun. Okay? Yeah, I know. I'm weird. Okay? But look, the point is, why is graphite slippery? Because guys, this is what I think is so neat. These layers, okay, are held with these white bonds that are considered pretty weak, and the layers literally slide past each other like this, okay? Compared to the diamond, does it look like there's room for electrons to move around? Yeah. Graphite will conduct electricity. Don't put your pencil in the electric socket. Okay?
Wait, so can we do locksmith lead or graphite except with our pencil?
If you took all the as much pencil lead as you could and put it in like a mortar and pestle and ground it up, then yes, you can do that. Okay? Now, the difference. Why do we have such crazy differences? Okay? Guys, it's all to do with how they're held together. Carbon is very tightly held together. Graphite, those little hexagonal circles are held tightly together, but the layers are not. Okay? So and coal has no structure at all, sorry. Coal, we get it, that's his name. He's boring.
Amorphous and boring.
Amorphous and boring.
Don't let it say your lunch table.
Okay? So diamonds, excellent insulators. Okay, graphite.
Wait, do we need to know this?
I mean, I would look at it in the notes, but you don't need to worry about writing all this down. Okay? Guys, this is what graphite looks like under a microscope. You have these hexagons in these layers, and they slide. Okay, they slip and slide. All right. Let's wrap up this section. Okay. Tell me one more time, what does this word, if you see the word molecule or molecular, what do you think? Covalent. Covalent without a dipole. Say it in another way. Something covalent without a dipole. A nonpolar covalent molecule. Okay? Folks, nonpolar means it has what type of intermolecular force only?
London dispersion.
London dispersion. There are no polar bears in London. I can't claim that for myself. And then someone's always like, yeah, but what about the London Zoo? Fine.
You fail that person.
Sorry. Okay. Let's bring this all together, people. Would you say London dispersion forces are strong or weak? Okay, weak. If something is held together very weakly, does it take a lot of heat or a little bit of heat to break those bonds?
Little.
Just a little. They're very weakly held together. Okay? Well, tell me this. For elements and compounds that are held together with London dispersion forces only, do you think they have high or low boiling points or melting points? Very low. So guess what? Most things that are non-polar, that have London dispersion forces only, are gases at room temperature. Okay? Think about it. If things are easily melted, easily boiled, room temperature is almost too hot for them. Okay? They're already in the gas phase by the time we get to room temperature because they're easily pulled apart. I want you to look at your halogens, for example. All right? Group 17. Think about Brinkelhoff. F2, Cl2, Br2, I2. In case I've never mentioned it before, this periodic table that we have on the wall, the elements that are written in color, they're colored in orange, are gases at room temperature. What do you think it means for the two elements that are blue? They're liquids. There's only two liquid elements at room temperature on this entire table. Is a solid. And anything that's written in gray is a solid at room temperature. Look at your halogens. F2, Cl2. They're gases. Why is it that bromine would be a liquid and iodine is a solid? Think about it. Think for just a second. F2, Cl2, Br2, I2. All of those are nonpolar. All of those are held with London dispersion forces only. Why is it that those London dispersion forces are slowly but surely getting a little bit stronger as we move down? What's that $1,000 word that I told you to put exclamation points on? Polarizability. Okay? Here's the deal. Okay? This entire slide, we're talking about things that are non-polar. Your Brinkelhoff elements are really a good example. The larger the atom or molecule, the more polarizable that molecule is. Okay? I have seen questions on the AP exam like F2 versus I2. Which one has the higher melting point? What are you going to say? I2. Why? What do they have in common, first of all? Besides that. Okay, although both molecules are nonpolar, which means they have what type of force? They only have London dispersion. Why does I2 have the higher melting point? It has more electrons, which means it's more polarizable. Okay? You can just put it on the counter for now. If it does have a dipole, then you've got other things at play. Okay? But I want to make something abundantly clear. We're wrapping this up. Of your three intermolecular forces, which one is the weakest? Okay? LDF. There we go. What's next? Dipole-dipole. And the strongest of the three would be hydrogen bond. Can you please tell me, where do intramolecular forces fall in this spectrum? Are they stronger, weaker, somewhere in the middle? Okay. Tell me this. Which is weaker, covalent or ionic? Covalent. Okay? Let me be sure, I want to make sure this is clear, ladies and gentlemen. Okay? Intermolecular forces, okay? This is their order. But guys, intermolecular forces are not even in the ballpark with how strong intramolecular forces. I'm not even going to write the word covalent here because it is so far. Let's put covalent there. Sure, have your nose. So covalent bonds are stronger than any intermolecular force. And let's even go further, ionic. Ionic bonds are super duper strong. That's a technical term. So tell me this. In this spectrum, what kind of compounds are going to have the highest melting points? Correct. Have you ever seen liquid table salt?
No, that would be awesome.
I haven't. I'm not talking salt water. I'm talking melted, molten NaCl. No. You know why you've never seen it? It does exist because the temperature to melt it is like off the charts. Your oven is not even close to getting hot enough. Okay?
The sun.
Huge melting and boiling points. Okay. Ladies and gentlemen, this is where I'm actually going to stop. We will pick up here next class.